Okay. So like we were saying, we sort of learned a couple of things, and we did this delta y conversion, we gave it to you. Well, you must have done it, so this mesh analysis is there. So today what we are trying to do is to start from where we stopped, do a little problem from this mesh analysis, and then go out and do some other analysis methods, so that we are picking up certain amount of tools to analyze circuit related problems. So let me take the first question. Okay, let me take the first question. It's out of the book. Now this book and the book that I am showing you are two, I guess, different things, because sometimes the question numbers may not be the same. This is the question that we are going to answer. Let's make it, okay, it doesn't matter. Okay, fine. So we are supposed to use mesh analysis. We all know. But you look at this, it's kind of, fallen on one side. We are used to seeing the little ground TV hanging from the bottom. All the batteries are nicely placed, so we are used to looking at it like that. But here, somebody has pushed it over. It has got clicked. You can do the problem like this. This is a regular experience, you can do the problem like this. But however, if you are not comfortable with this, redraw it in a way that makes you happy. Right? Now I'm almost sure if I take this and I draw it again, redraw it, it's definitely going to make you a little bit more happier, because if we put it like that, see, now this is something that you have seen before. Yes, so I got to move this up by about 90 degrees rotated. I get this, then this would be E2, that would be E1, this would be R3, that would be R4, this would be R2, and this would be R1. Perfect. This looks better. Yeah? Now we analyze it. So how would you do now? I'm not going to write the steps of how this is going to be done, but on the other hand, I would do it in what happened here? All of this is messed up. Because I want to make sure I do exactly the same things that I did for the previous group, so that you don't feel cheated, right? You want to do the same thing. Okay? Now this is question number 8.23 in the book, right? Now somebody told me that the book doesn't have question 8.23. I actually looked at the book. In fact, yes. Usually when you turn the book into chapter 8, and if you go to end to look at the problems start from 8.1, 8.2, 8.3. This book doesn't. This starts like basically 1, 2. So you have to first of all find out the chapter, then inside the chapter, I guess 1 means 8.1. So please don't say I couldn't find the problems, because it's there. So now the step number 1 is what? Look at this. How many loops? Immediately the square theory comes into your head. 2 loops. Done. Each of the loops need to be marked with the loop current like this. Since there's 2 loops are there, 2 loop currents are marked. That's done. What do you do next? Step number 3 is if there is any ambiguity in, I guess, which way the current is going to flow through a particular branch, you got to take a release ambiguity. So you look at R4, no ambiguity. There's only a single loop current that goes through it. Perfectly okay. We start marking which way the voltage drop is, because why? If I do that, it will make it easy for me to add it algebraically. this goes up, so the voltage has to be marked going down. Here, this is plus minus, we know that this is plus, that is minus, that's the way it has to be marked. Here, you have R3, no problem, only this one is going through that. Voltage drop goes this way. Here, you have a branch that is going to be common to like, I guess, both loops, or common to like more than one of the loops. Hence, you have an ambiguity. Let's mark this one as capital I1. Immediately we know capital I1 is equal to small I1 take away small I2. You don't have to write it down. If you can keep it in your head, fine, right? It's easy to write it down because then you don't make a mistake. And then R1, there is no problem. This going this way. See, the loop current is going through this particular resistor in the clockwise direction. Hence, the voltage is marked anti-clockwise. This one, that is plus, this is minus. The voltage is marked down. And then here, we have put this going down, so the voltage so I mark it up. Now I done the step number 3. Step number 4 is to apply the Kirchhoff voltage law. So immediately I will say Kirchhoff voltage law applied to the first loop in the clockwise direction, indicating which direction is going to be positive. I apply. So I start from here. Maybe I start from here. I have E2. I'm going through the loop. This is opposite to the loop. So in fact, you got algebraically it is I1 times R3 and it's minus. This is also opposite to which way I'm going. So it's minus. It should be capital I1 times R2, but we know I1, capital I1 is going to be simple I1 into simple I2, R2, and this is also going in the opposite direction. So we have I1 R4, and that should be equal to 0. That's the first equation. Then we apply Kirchhoff voltage law to loop number 2 going in the clockwise direction. This is that loop. Start from any place. Let's start from here. That is to be capital I1, right? That should be capital I1 times R2, but we know that it is going to be simple I1, simple I2 into R2. This is going opposite to the way I'm going. I'm going in the clockwise direction around the loop. So this is I2 times R1. That is plus E1 equals to 0. Right? Now I got two equations. Now we got to make it look nice. I'm sure you can do the algebraic manipulation to make it look nice. I will directly take it off this. It says I1 R2 plus R3 plus R4, right, minus I2R is equal to E2. That is the first equation. And the second equation that you are going to get out of this is minus I1 into R2 plus I2. You have R1 plus R2 is equal to E1, and that is the second equation. You had two loops, you got two equations. How are you going to find the answer? For I1 and I2, Cramer's rule. You know how to apply that. Apply the rule, Cramer's rule. So if we apply, apply the Cramer's rule to this, right? No, if you not apply, we had to first of all put it into a, I guess, matrix form. Once you do that, you can then apply what is known as the Cramer's rule. So here I got R2 plus R3 plus R4 and like minus, what is this R? R2. R2, this is minus R2, and this would be R1 plus R2. We have a matrix. Two variables would be I1 and I2. So if I expand this, I would get this equation from the top. If I expand this, the second row, I will get this equation, and that is equal to E2 and E1. Once this is done, immediately if I want to identify I1, I have to get the determinant. Since this is the first variable, I have to substitute the first column of this with that. So it should be E2 E1, right, minus R2 R1 plus R2 over this whole thing, actually, right, determinant R2 plus R3 plus R4, and this is minus R2 minus R2 R1 plus R2. There you are in terms of amperes. You can find the I2 by substituting that into the second column, where you would get I2 to be equal to the determinant of R2 plus R3 plus R4 and minus R2, and that would be replaced with this determinant whatever is here. So these also in amperes. You found the I1 and I2. Now once you find the I1 and I2, any other variable or any other thing in the circuit can be found. So this is not rocket science, right? If you do a couple of problems, a couple of different configurations, you should be okay, right? You should pretty much okay. Now, so this is what we did previously. We are also going to do this. We had a problem on like supermesh. We're going to do supermesh also, but before that, I want to ask you a couple of questions. Right? Now to ask. Now, of course, you are going to realize that I am going to cut and paste chunks of stuff that I do into pages, and you will never be able to keep up with that speed. So, I guess my advice again to you is take down the stuff that I am saying if you feel it is important. Go home and you are going to basically reconstruct my lecture note. That gives you an advantage because why? You are going back and looking at what I already taught. So let's take this one out, right? Let's take this and put it on a new sheet. Then also let me take these two equations and put it over here, right? Now everything is perfect. Okay, let me take out what is some things that are not necessary. Oh, I can't take it out. Ooh, that's bad. Okay, fine. Right, we got this. Now I want to arrange this in some form. So let me take this portion of the equation and move it up here so that these I1s are base aligned and I2s are also going to be base aligned, and this equal signs are going to be aligned. Right? Now if I look at this, I clearly see in these equations 3 different segments. Right? 3 different segments. I see a segment here, see? I see a segment here and I see a segment here. 3 segments. Look at the first one. First column talks about basically what? Basically I1. Talks about I1. It has some coefficients, but it primarily talks about basically I1. The second column talks about I2. Third column, I voltage source. Now we are beginning to see some structure in this. Let's look at the first row. Now you realize the first row, you see the first row was about loop 1. See, loop 1. And the second row, I mean probably the way we obtained the equation was looking at loop 2. Now let's look at the first one, first here. Now if you look at this, you realize this I1 in the first loop, this gives me all of the right resistors which are going through I1. Sorry, it will give me all of the resistors where actually I1 is flowing through them. Just take a look at that loop of I1. You realize R4, R3 and R2 are all hit by I1. Right? So that's what comes out as the coefficient of I1 is R2, R3, R4. Right? Now look at the second. Sorry. So now take a look at I2. Now basically the component there tells you if you are in loop I1, you are in the loop I1, what contribution does I2 give? It's the interaction with the other loop. Now you realize this I1 goes in a clockwise direction, whereas with respect to that, you realize I2 goes in the opposite direction. And if you are in this loop of I1, the only other loop that is going to go across this loop is to basically R2 and I1, R2 and I2, because R1 has nothing to do with the loop I1. But the only thing that has something to do with some other loop is R2. And inside R2 also, the current I2 is flowing opposite to I1. That's the reason why here you have a negative sign. That's the reason why you have a negative sign. So this gives you the contribution from some other loop to the loop number 1. Right? Okay? Oh, what happened here? Right? So that is there. So now now let's take a look at the loop 2. Now when you are in loop 2, you are here. So this one, right? So actually this is loop 1, this is loop 2. Right? So you realize loop 1 and loop 1 talks about the loop 1. Everything associated with loop 1. Loop 2 and loop 2 talks about everything associated with only loop 2. And everywhere else outside that talks about the interaction between a loop 1 and loop 2. Right? So here you are talking about if you are in loop 2, what is the interaction that I am going to get from the first loop? So I look at the resistors inside the loop 2. Loop 2 has R2 and R1. But out of R2 and R1, the only one which is going to be common with the loop 1 is R2. Right? With R2. But also in R2, this is going clockwise and this is going up through R2, but the I1 is going in the opposite direction. Hence, you got minus I1 and R2. This gives you the interaction with the other loops. If there was another loop with some other resistor, that also has to be taken into account. We'll look at that later. Here, this shows only about the loop 2. You have I2, you find out all of the resistors that are hitting I2. As you go along the loop, you realize, right? As you go along the loop, you will realize there is R2 and R1. Both of them are hitting I2. That's why the R1, R2 came. Right? Now, basically over here, you have the E2 and E1. If I look at now, what you have here would be the voltage sources of the first loop. So I go around the loop. This is going what? Basically with the loop, E2. There are no other sources in there. That's the reason why this became E2. Then I got the loop 2. I go around the loop 2. There are no sources, there is a source. And it's also going in the same direction as your loop. Hence E1. Now you don't need Kirchhoff law, do you? You can just look at this and then write down the equation. This is what is called the format. Right? This is what is, if you look at the book, that's format approach. There's a format. Now the question that you have to ask yourself is why this? Right? Why this? Now you realize any small equation, any small circuitry, you can write the equations, solve for the determinants and find the answers. But you realize that as you go up and come to the campus level, university level, what you are going to handle would be large circuits, meshes with about 100 different, you will get a huge network with about 100 meshes, right? Each mesh will have a loop, current that is associated with it, and each of them will generate an equation. How many equations would you have? 100 equations. How much would your, determinant be? 100 by 100. You know how to find 100 by 100? No, you need a computer program to do that. How would you tell the computer program that this is your circuit? That's a problem. So you need to have, you can't tell the program, go apply Kirchhoff voltage law, then you get the result. Yeah? Computer program, sure. I know how to apply it. You can't do that. So you have to abstract yourself and find a different sort of method to find it. This is the method. Now here, I don't need to know a spot about Kirchhoff law. I don't even have to know there was a person called Kirchhoff. I can just write this down looking at this. I'm going to do an example. No Kirchhoff, write it down. Because of this, we don't give it an example. Why? You want to test your Kirchhoff laws, right? You are not going to look at it. You say, forget about Kirchhoff, I will write down the equation. You can do so, but we need to know how to apply the Kirchhoff law. So the arrows and all that stuff has to be given to us before we give marks. So we don't ask this at exam, but we need to know this, right? But let me do an example and then show you, what circuits are used with this method. Right? So let's take an example. Let's take a very simple example. What did I take for the other guys? I don't know what in the world I have done here. Oh, it looks crazy. Here. There you go. I took this one. That's what I did. So let's take some arbitrary circuit, save, take it up here, do the hopping, we will apply the format approach to find the answer. So first of all tell me what is so the first thing you do is what? You identify the two loops. Perfect, there's two boxes. Each loop is marked with a loop current like so. That's it. Now we'll start writing the equations. How would I write the equations? I have loop 1. Of course, if I ask you at the exam, you would not write loop 1 here. I'm just writing it because you know it's loop 1. And this item is what? About the loop 1. So, you have I1 going through the loop and each and every value of the resistor that hits this one has to end up here. So, this R1 is hit, R3 is hit as you go along the loop. So, this one would be R1 plus R3. Then I have plus or minus, I have I2, right? So, basically what you have in I2 is if I am at I1, what contributions through certain resistors would I get to loop 1 from any other loop. So I look at this, this loop meets that. This is the only resistor that is going to be common between these two. I am going over here in this loop in the clockwise direction, whereas I2 goes up here. This goes down up here. So that means it is minus of R3. See? And that should be equal to what? As I go along the loop, what are the voltage sources? So I go along the loop, you realize this is going this way, this is going that way. So if I go along the loop, this is going to be 10. And when I come down, this is also going in the same direction as my loop. So that also gets added up. So this is E1 plus E3. And if this was in the opposite direction, that would have been minus. Then I look at this one. This is loop 2 with loop 1. Now this is you're at loop 2. I want to find out what contributions am I getting from other loops. So here I'm going in this direction. This is not going to be common with any other loop. This is the one that is going to be common with any other loop, but this one I am going this way, the other one is going that way. That generates a negative in there. That's I1 is the one that is going to contribute, and the resistor is R3 that is being contributed towards loop 2. Then I have plus, I have I2, I don't know where this plus, I'm going to look at it. Now I look at the loop 2. What are the resistors that are hit by loop 2? As I go along, I see R3, I see R2, right? So this is R2 plus R3 equals. Now I go around the loop to see what are the voltage sources. This is going in the opposite direction. So this is minus C3 because I am going in the clockwise direction. See, I am going in the clockwise direction. Right? I am going in the clockwise direction, and this is going opposite to that. So this is minus C3, and I go around the loop. This is going up. Again, it's going opposite to the way I am going. So this is minus E3 and minus E2. That's it. Now apply the Cramer's rule. Do the needful. You are going to go home and do this problem with our regular way of handling this using the 6 steps. Find out whether you get the same answers. Right? You should. And that is what is called the format approach. So are we happy? Yeah, now we know of a very quick way of finding out whether our answers are right at the exam. Do everything, finally got the answers, check it with this, the format, and you're okay. Now, so this is a sort of a revision for the previous week's problem. Now I have to look at some ideas. I seriously need to have organized this before I came here. Right? This looks very messy. Here, I think what I did next for the previous class is ask a lot of questions. Here are the questions that I'm going to ask you. Right? Now, we'll take for example, I have a circuit like this. I have 2 resistors which are going to be in parallel. This is R1, that is R2. Using your advanced level sort of knowledge, could you tell me whether these 2 circuits are equivalent? Yes. Stupid question, but yes. Answer is yes. Now, so you realize that by taking 2 resistors which are going to be in parallel with each other, you flip it, there is no difference. But if I have 2 resistors here, and if I have 2 resistors here, right? This is R1 and R3, and this is R3 and R1. Is there any difference between the circuits? Huh? Oh. It's not minus it. Is that different? Yeah. So by switching the 2 resistors up or down in the same branch, no problem. This is it. Now let me take it a step further. Basically, if I have a circuit like this, This is R, E and I, and if I change it to this, now do we have any difference in the circuit? Are those two circuits equivalent? Yes? Same. Everything is same. It's the same. So ultimately now we know as a conclusion, anything that happens to be two branches which are going to be parallel. If the branches, I don't care what is in there, it's still the same. What will happen if I change this R and E? If I flip the R and E, would there be some sort of a difference? Okay, so if I have it like this, should there be a difference? Is it different? No, it's not different. Another rule, inside the branch, any item can be moved up and down, as long as there is no node in the middle. Right? Of course, if you had something like this, that is not equal to something like that. You cannot flip these two. Now that you can't, because why? Now the calculators and the branches, all those things are going to change if I flip those. In a single branch, with no nodes in the middle, I can flip the items anywhere I want. Two huge branches, I can flip in parallel. Right? Now look. Now this is what is in the first couple of chapters. Okay, there's more. Now let's say, for example, I have a current source like this, which generates I1. We know what does that mean. I explained it to you last time. Current source means whatever happens at the output of the terminal, it injects into the circuit I1. I don't care what circuit you have on the other side, current is the same. Right? I1. You can't change it. Put that I1, completely I1 in your circuit. Now, let's take for example, I have a second current source like that, which will generate I2. Now, I2 also says, I am I2. I will not give anything less than I2. I2 is I2. What happens if I connect these two together? The first question you ask yourself, am I able to connect it like this? He says I1, he says I2, can I connect it like this? So yes or no? Who says no? Nobody says no. Yes, you can connect this. So if you connect it wrong, burn. Right? So how about you? You see what happens? Yes. If you apply the Kirchhoff current law to this branch, he holds it at I1. I don't care. He doesn't have another branch. Then the second branch, other branch, he holds it at I1. He doesn't care about the branch. He drives I1 out of it. Then what happens is, if you apply the Kirchhoff current law to that surface, immediately you know that I is equal to I1 plus I2. You can do this. The second question, if I have a current source, I put another current source like this in the same branch, what is I? Yes. I1 plus I2. Somebody else? This is your opinion. I1 plus I2. Anybody tell me? What's your opinion? Yes. You connect like this, again, one gone. Because why? Here is a fundamental rule. What is the fundamental rule? Inside the branch, the current source is going to keep the current flow fixed. That's what you know. Remember I told you, A level, whoever the teacher comes and does the problem, you concentrate on the problem. And if the teacher does, I don't know, some amount of N class round problems, then at the exam you get M problems, which is M is like less than N, you are okay, you pick it, you are great. And you think you are very great. University level, don't do that. University level, you have to understand the concept. What is the concept? Concept says, in a branch, this current source is going to keep the current flow fixed at I. Now you got two of them. This is like we drive on the highway. The guy at the dog, and we coming from the can't do that. Right? Both have to either go at the same speed or something should happen. So you can't do this. Never connect two sources like this. You want to connect things that are at home, don't connect the lab ones because they are very expensive. Connect anything, but not the ones in the lab. Because you do this, there will be smoke coming on, you'll be watching, oh, there's a party going on with smoke. Don't do that, right? Can't connect like this. So ultimately what you have here, you have one rule. What is the rule? You cannot connect current sources in series. That's the rule. Chapter 4. Right? You saw it. Chapter 4. Right? This is there in chapter 4. I will also ask you the same question by placing these sources, current sources, with voltage sources. Also, on the other hand, I will be able to connect the two voltage sources that are in series. Now, what will happen in the first circuit? You know that if you pick a voltage source, I have told you as a rule, as a fact, that the voltage that is going to be that is going to actually exit the two nodes is fixed at E1. So this is fixed at E1, this is fixed at E2. If I connect them together, this is what will happen. If E1 is greater than E2, this goes. If E2 is greater than E1, this gets busted. Can't do this. Right? Because why? There's a rule that says in a branch, if I have this as only voltage source in a branch, those two nodes at the end is fixed at that voltage. Can't connect. You can't have two voltages connected. So this you should never do, especially with the ones in the lab. This one you can. This one you can. Here, this is E1, this is E2. Can you tell me? What is V1? E1 plus E2, right? E1 plus E2. If you are going to, so in fact, this is E1 plus E2. This is completely acceptable, right? Now, let's get on to the problem I was talking about. If I can locate this thing. Here. I don't know what in the world happened here. Here. This is question 334. This one, right? Question number 4. So let's cut this out. Okay, this is question number, I think, 8.4 in the book. Question 8.4 in the book. Tell me, part number 1, we are trying to analyze this using the mesh technique, right? Mesh analysis. The first part of the question asks what is Vs. I asked this question from the previous mesh. Vs, immediately the gentleman said, it's the voltage across the current source. Is that correct? Yes, correct. Right? I said, I know that. So before you say it, I said, I know that. But what is Vs value? Yes, what is the value of Vs? Hmm? 24. Why? Parallel. So why? Yes, he says it is 24. Huh? Question is why is it 24? Huh? That point is here, and what's the other one? 24. No, it's not because of that. It's because why? If a branch has a voltage source, the ends of that branch is fixed at that voltage. That's the reason. That's the reason. Now that reason we need to know. So anywhere we can apply. It's 24. Because why? The voltage source at the end of the branches like this pipe. What happens outside in the circuit? Still 24. You need to connect it a voltage source or current source, whatever the source is. Of course, you can't connect it across a voltage. You can connect it across a voltage source with the resistance, not with the voltage source. Current source, sure I can. I said what? Inside the current source, the current is fixed, whereas the V is not fixed. This is the reason we use in the mesh analysis to say that we cannot apply the Kirchhoff voltage law across a current source because it is dependent on the extraneous activities that is happening in the circuit. So here immediately we understand Vs and we also understand the reason it is equal to Vs. Sorry, it is equal to 24 volts. Now the second part, B, is to apply the Kirchhoff voltage laws, to apply mesh analysis to find the I1 and I2, or maybe I2 and IS. How do you apply it? Go through the rules. First is identify the loops. How many are there? 2. Done. 2. This is I1. This is I2. Perfect. Is it perfect? This is more than perfect. We don't know it yet. More than perfect. I have to apply the Kirchhoff voltage law to the loop 1. This is the loop 1. Now what is the problem? Huh? Yes. There is no resistor. Oh, who cares? Here's the good part. Yeah, I don't do whatever happens. We have a rule that says if a branch has a current source, the branch current is held at that value. So I don't care what happens. If the loop current is I1, I know I1 is 2 amperes. It can't be anything else. Why? Because we just now told you a rule. Now we don't have to apply Kirchhoff law. It's 2. Isn't that easy? Fine. So I1 is 2 amperes. That's fine. So we don't have to have 2 equations, no Kramer, nothing. I have I1 being equal to 2 amperes. Then I2 I can find using the Kirchhoff voltage law. Because why? You see, in that loop there is no current source. No current source. So I will now use my technique. What is my technique? Mark the voltage drops and then apply the Kirchhoff voltage law to loop 2 in the clockwise direction. I have E, right? You get minus I2 R1 and minus I2 R2 being equal to 0 is the Kirchhoff law. That is the second equation of the loop. And then immediately I can calculate I2 is equal to E over R1 plus R2, which is equal to 24 over R1 plus R2 is 1 plus 3, this is 4, that is 6 amperes. Isn't that good? This is absolutely brilliant because I don't have to apply a Kirchhoff voltage law to the second loop. Now let me ask another question. Tell me, would your answer have changed? Tell me, would your answer have changed if that branch was replaced with a resistor and a current source of 2 amperes? Would your answer have changed if I have replaced that branch with a current source and a resistor? Would it have changed? He says no. You say yes. What do you say? Would it have changed? Would your equations have changed? Would your opinion on I1 being equal to 2 amperes change? Yes or no? Listen, right? Now the rule. What does the rule say? The rule says, I don't care what is in the branch. If there is a current source in the branch current is held at what? The current value of the source. You can't say that. Even if you have the resistance with 10,000 K, branch current is what? Still 2 amperes. Can't change that. So your equation would not have changed at all. Still I1 would have been 2 amperes despite you having an R3 there. Now did we understand this? You need to understand this because that's what I'm going to give you at the exam. No, I don't know. But it's good to know this something, right? It's kind of good to know this. Right? So it would not have changed the opinion on the calculations, nor would anything here change. Still you would get I2 which was 6 amperes, I1 is equal to 2 amperes. Now immediately you can now calculate basically value of I2 which is going to be equal to 6 amperes, and you have there, you realize base IS is equal to I2 minus I1, and this is basically 6 amperes minus 2 amperes which will give you 4 amperes. Right? Are we okay? Right? Now I'm going to do a little change. Now you already told me that if I change 2 branches which are parallel, nothing changes. Yeah, you have told me that. Now I'm going to do that. I'm going to change the 2 branches slightly. So here's how I'm going to change it. I am going to bring this voltage source to the outside edge, right? And take the current source in, and I put in my 2 resistors. That's my ground. This is E, that is I, right? This is R1, this is R2. Did I change anything? No, I didn't change anything. I switched it, but I didn't change anything else. Now, in fact, in your analysis method, this has not made any difference. When you told me this is not going to make any difference. The entire branch, if they are parallel, I can shift it. Now I will apply the, I guess, mesh analysis. What would I do? First thing, look at this two boxes, two loops. Mark the loop. Currents there is I1 and I2. I1 and I2. No problem there. Now I start applying the Kirchhoff voltage law to each loop. I go to the first loop. Yes, what's going to happen? Yes, what's going to happen? How do I apply the Kirchhoff voltage law to loop number 1? Now what of a sudden? There is a current source in that loop. Can't apply. Then there is, go to the second loop. In the second loop also there is a current source. Now this is what we were talking about when we stopped last time, saying that this is what? Not that. It's the super mesh. Super mesh, what did we do? We dropped that offending source and said super mesh. Is that what we said? Yes, that's what we said. Now, here you clearly understand how a super mesh is formed. Though the circuitry is the same, identical, the super mesh is formed because of why? Two loops have a common branch. Two loops have a common branch with a current source in it. In the previous one, where you had the current source was not a common branch. If your current source will end up in a branch which is not common, your problem becomes uncommonly easy. One equation was dropped. See, you saw that. Here, it is in the common branch. The moment you have it in the common branch, that is when you have the super mesh, and you drop that part of the circuitry, and for the part that you drop, you apply the Kirchhoff current law. Because in that mesh analysis, you apply the Kirchhoff voltage law. For the drop part, you apply the Kirchhoff current law. So immediately from here, we can identify that, right? We can identify that this is the source, that this is basically the source, that offending source. We drop it and we recreate the circuit, I guess, without that, and we analyze it. So here you are. That's the circuit we will analyze. This is I1. Still this is the same. Only part is dropped is here. That portion you have I2 as the current that is flowing. This is I2, R2, that is E. Now we apply the Kirchhoff voltage law to this super mesh. Big one. So how do we do it? Just like previously, you mark all of the voltage drops. We're going this way, that's why it's going that way. And we apply the Kirchhoff voltage law to the super mesh, which is written as 1 and 2. There is no rule like this, but I like it. Huh? Nobody said no to me, so I am using it. Yeah? If I publish a book, then they say, what is this? But anyway, right now, 1 and 2 means to me, I apply it to the super mesh. Then if I apply it to the super mesh, I have E, which goes in the same direction of my loops. Then I have what basically minus I2 R1 and minus I2 R2 is equal to 0, and from that I will get I2 is equal to E over R1 plus R2, and we already know E is 24 and R1 is 1 and R2 is 3, which will give me the same answer as previously. Right? Then then also I have to apply the Kirchhoff current law to this particular part that I have dropped, which means capital I should be equal to I2 minus I1, because I2 is the one that is going up, I2 is going opposite, and then immediately from this I understand 2 amperes is equal to I2, which is 6 amperes, take away I1, and I1 turns out to be 4 amperes, just like previous. Now, there is nothing to stop you. If I give this question at the exam, there is nothing to stop you from switching this entire voltage source, entire current source and the voltage source, flip it, because we have already told you that flipping is not going to change anything. If I flip the whole branch and make sure that basically the current source ends up on some outside region, not on a common branch, and your problem solution becomes easy. Right? Now there are some questions I don't specify which method you have to use. In a case like this, if you do a trick like that and answer the problem very quickly, you get 25% more marks. So you get 125 out of 100. Yeah, sure, you can do that. I have given it. I have some people have done some ingenious methods. They got 0 for that. Because in the question paper, if I ask you to do it using a specific technique, don't try to be a genius. Some people I ask them to do mesh, they say node is easy, I do node. Then they fail. They ask, why fail? I did everything right. Some questions I don't specify the method. Then if you do it in some ingenious method, these are our concerns, but let's say ingenious method, right? You get more marks, which is very good, right? Good for you. Right? Bad for me because everybody would try some ingenious method, and I have like in my entire 400 papers, I have N+1 ingenious methods I have to check now. So my marking becomes low, right? But anyway, this is right. So we understand where this is coming from and how it's going to apply. So that will bring us to the close of mesh analysis. Is that good? Well enough. Now there's another method that we're going to learn. We might go for a tea break and then come back and do this. So let me start. Let me try to take you back to this last lecture and take some items from that and reiterate their, I guess the basic importance for the next section. Here, let me show you some of the things from the last lecture. Now, ladies and gentlemen, if you do not understand anything here, it's very important that you tell me, right? In the school, in your schools, right? If there was a teacher teaching something and the teacher makes a mistake, and you highlight that mistake, goodbye child. Yes, the teacher will harass you for years to come. That happens in schools, right? I remember we had a teacher like that. The old teacher, of course, he did not know how to harass people. If he tried harassing, he would get harassed. So when he used to do something on the board, right, and then all of a sudden he makes a mistake, right? I was a quiet person, so I didn't say much. But the next step, 2 years, he did not know half the stuff that happened, but when there was a mistake, he knew that. So he said, shut, then you confuse the guy. So the guy looks at it like this, and after that, where are you marketing? And he wipe off the book. And then after that, he asked, Varadatir, until that guy just stops coming to class. Right? But at university level, we don't do that. Right? If you say it's wrong, he would even give you the pen. Here, come and show us how it's done. Yeah? I know you people are waiting for this. Let me show you how it's done. Yes? tell us what's going on. Because why? Not like the school, you have 12 weeks and the weeks are going on. All of a sudden you have learned 6 different aspects of circuit. Today at the end of the day, there will be almost 9 various aspects. By the next day, you get a holiday, no? Tomorrow is the holiday. Holiday, right? You thought holiday. Right? Tomorrow we have lectures in the afternoon. So you do all of that put together, you will immediately sort of rack up a lot of information. So unless you tell us exactly what's going on, we will not be able to change things. So who are the bashers now? The one you, right? So you can tell him. He will put it sugar coated, sugar coated, you know. You can come and tell me this is all wrong. Right? And there are mistakes. I mean, there have been times when I was wrong. You know, I do some algebra, something like that, all went haywire. And sometimes the student comes and tells me, sir, over here, if you did it like this, it would have worked. I come back next time, and I tell that gentleman is about to told me how it was done, and here's how he showed me. He can do that. Yeah, we have now come to a level, we understand that we don't know everything. Right? But we have to know something. We don't know anything. Yeah, right? So let's go for tea and come back.